We have seen previously that in multi-agent environments, okay, where more than one agents are, in the game, the situation changes. What kind of problems arise? And then we try to plan our world according to not just our needs, my needs, but also the impact of others, working in there as well, who are planning, so to speak, against me. Okay, and that's where the word adversary or opponent comes in. Okay, we have studied search strategies where only single agent, as I said, you're the only one, you decide good, bad, right, wrong, nobody affects. Okay, but multi-agent, yes, there are people who don't want you to succeed. Let's put it this way: they don't want you to succeed, and you don't want them to succeed, and that's the interesting part. Okay, and of course, this usually occurs in games. The important thing to remember is that every agent needs to consider the actions of the other opponent, the adversary as well, because it might affect its own performance, and it will try to preempt the move as well. So I may be playing a game where I want to win. At the same time, I also am at the back of my mind, you're thinking, all right, if I can't win, I must make sure that the other opponent should not win as well. So there are two kinds of things you need to understand. One, can I reach my goal? At the same time, protect myself against the other's move so that I don't lose either. Let's say if I can win, say for example, in 15 moves, playing a chess game in 15 moves, right? And I can reach my goal, but I need to be also clear that during, let's say, in the 11th move, the opponent attacks me and attacks in such a manner that I can't even complete my other four remaining moves, right? And that's the interesting part. So all the time I'm thinking of attacking as well as kind of defending myself. In many applications, in addition to what we've discussed, there are many applications where we are searching, of course, for the solution, but maybe we want to get just to a solution rather than interested in it's a good solution or a bad solution. Okay, so opponents, posing each other, multiple agents searching for the solution in the same space with different winning strategies, different winning board positions, right? And with opposing goals, as I said. For instance, now let's consider a very popular game, tic-tac-toe. Some people call it knots and crosses. Now, in there, say player one might want that he should complete a line with all crosses, okay? Whereas the other player, player two, wants to complete a line of all zeros. Opposing uh, objectives, contrary objectives. So both have different goals. Now also notice that if player one puts a cross in any box, this reduces the choice for the other player, player two. So there are 9 open spaces in tic-tac-toe, right? 3, 3, 3. If I, as a player, if I occupy one position, that only leaves 8 for the other one. And then player 2, if it moves once, I'm now left with 7 positions and so forth. So every time my turn comes, a position has already been taken, right? But that's the way it is. Okay. So player 2 will actually try to anticipate my next move. And as I said in the case of chess, it's trying to win, at the same time making sure that player 1 doesn't overstep him and reaches his position of success. So, so people try have in most cases in these games, people have already predefined strategies in winning those games. And I can assure you, if you haven't played this before, go and do it now. In about 10 or 20 or 50 games, you will know the real strategy. And so will your opponent. Now, the thing is, how will you preempt? And that's what the game is all about. Okay? And of course, intelligence is part of that. Many games, as I said, can be modeled as trees, as we've seen before. We focus on board games for simplicity. Okay, we have this situation where there's a node on the game tree representing a board configuration. Let's say position A. So from A, original board position, you can move to a new board position called B, or you can move to board position C. From B, you can then move to new board position D or E. And from board position C, you can go to F or G. Now, this might give you an indication of, remember, we've seen this before also, that this similar representation we use for showing traveling between cities. So you will also observe that this representation can be generic. It could mean to represent distances between cities. It could mean board positions, or it could mean something else relevant to the game itself. Okay, and both opponents are trying to actually find a solution that suits them. So games in AI, typically, they have sometimes you have perfect information, you know each and every move, you know each and every board position. Sometimes you have imperfect information, you're not sure, incomplete information is there. Okay, you have deterministic games where everything is very clear cut, the rules and everything, and they're very clear cut. And then there are non-deterministics. Okay, the important thing is that you know what the board situations are, you have a strategy, and you have to outgun, outthink, outmaneuver your opponent in order to win the game. I hope this was interesting. We'll see you next time. Thank you so much.